an opportunity to present our research work. So thank you to both of you for that. And yeah, today I'll be talking about one of my research papers, Robin splitting method for the Stokes-Biot fluid-poroelastic structure interaction model. So this work has been done in collaboration with Rebecca Durst, who was a postdoc over here at Pitt, Professor Annalisa Queni, who is a full professor at University of Houston, and of course my advisor, Professor Ivan Yotov. So some of the applications for fluid-poroelastic structure interaction problems include groundwater flow, petroleum engineering, blood flow, and industrial filters. So I will be devising my Robin method, and I will be checking my method on one of the applications, which is blood flow, because densities for the fluid region and the poroelastic structure for blood flow, like the ratio for that is close to 1. And whenever that happens, the regime always tends to suffer from added mass effect. So I want to make sure that my numerical method specifically works for blood flow application. And most of the work that has already been done in the Robin methods, they all check it on blood flow application because it can suffer from instability issues. Okay, outline. So I will begin by defining my Stokes-Biot model problem. I will talk about the motivation and some of the relevant literature that has been done in the field. Then I will go on to, develop my Robin partition algorithm, talk about the stability for the method and time discretization error. So we are getting first order convergence in time, and we were able to get that numerically as well. So theoretically and numerically, we are getting the same results, which is a very good thing. And after defining my Robin partition algorithm, I will go on to define my iterative scheme. Robin iterative scheme proved that this scheme converges to some monolithic scheme. And then I'll talk about my monolithic scheme and finally some of the numerical experiments. So first numerical experiment is the convergence test. I will, take all the physical parameters equal to 1 and check for the convergence of my method. I will also talk about robustness of my Robin parameter, like which values of Robin parameter they are perfect and, where, yeah, like for which particular values of Robin parameter my scheme won't work. And finally, the blood flow application. So yeah, I will also again be talking about the robustness of Robin parameter over here as well. So in my numerical experiments, I will be conducting these experiments. Conducted these experiments on 3 schemes, which is the Robin partitioned algorithm. Second is the iterative algorithm, and third is the monolithic scheme. And like compare what kind of results all my 3, algorithms are giving me. Okay, so I'll start by defining the model problem over here. So we have omega as the spatial domain. So the top domain is the fluid region omega F, and the bottom domain is omega P, which is the poroelastic structure region. We have some of the notations. UFPF is for fluid velocity pressure, sigma is F is for fluid stress, eta P is for the displacement, UPPP is for the Darcy velocity and pressure, and sigma P is for the poroelastic stress. So my fluid region omega F is governed by the Stokes equation. So first I have the momentum conservation equation. FF over here is the body force term and rho F over here is the fluid density. Mass conservation equation. Okay, QF over here is the external sourcing term coupled with some of the boundary conditions. So we have Neumann stress boundary condition and the Dirichlet boundary condition. So we'll be making use of all these partial differential equations and boundary conditions when I devise my numerical method. Next, we have the fully dynamic Biot system governing the poroelastic structure region. So first, I have the Darcy's law. So mu F over here is the fluid viscosity and K is the permeability tensor. Solid equilibrium equation. So FP again is the body force term and rho P is the density of the structure region. Solid mass conservation equation. So QP again is the external source of sink term over here, coupled with some of the boundary conditions. So we have some Dirichlet boundary conditions and the stress Neumann boundary condition, and along with this Neumann boundary condition for the Darcy equation. So we will be making use of all these boundary conditions when I will be defining my numerical method. Next, so okay, now to make sense on the interface, since we have these non-overlapping regions, we need to make sure that all the equations, they are continuously imposed. So we have these transmission conditions on the interface. So the first equation is conservation of mass, conservation of momentum, balance of normal fluid stress, along with the Beaver-Joseph-Safman condition. So in my numerical method, I will be using this no-slip condition. I'll be making use of all these transmission conditions on the interface to define my Robin boundary conditions. So these are extremely important for me. Okay, next. Okay, now motivation behind my research work. I'll be developing a splitting method for the Stokes-Biot. So first I'll be solving the fluid subproblem, and then I'll go to solve on my poroelastic structure subproblem or the Bio subproblem. Next, so the main motivation behind this research work is the added mass effect regime. So whenever we define a loosely coupled scheme, schemes like Neumann-Dirichlet methods, they always tend to lose stability whenever the density of the fluid region and density of the structure region, like the ratio for them, if that is close to 1, loosely coupled scheme like Neumann-Dirichlet method, they tend to lose stability. But when we use Robin method, we tend to gain back that stability. That's why. So this is the main motivation behind my research work. It is unconditionally stable. So we were able to show our method to be unconditionally stable. We have first order convergence in time theoretically as well as numerically. And this is robust with respect to physical parameters. And it is computationally less expensive than any of the monolithic scheme or any strongly coupled scheme. Okay, now some of the relevant work which has already been done in the FPSI Robin methods. So the first work by Bardia, Quani, and Quattroni, they did a computational study between the monolithic solver and and some of the loosely coupled schemes. So they compared Dirichlet, Neumann, and Robin and the monolithic solver scheme on a hemodynamic application, which is the blood flow application. They didn't do any theoretical analysis like stability analysis or the error analysis. It was just a computational study conducted, and they just wanted to compare the efficiency of all the methods. Next, this work by Martina Bukaj, Oikole, Seabold, and Tambaka. So in this work, they devised two loosely coupled schemes where they did the stability analysis. So for one of these loosely coupled scheme, they were able to show that the method is unconditionally stable, and for the second one, they were only able to show conditional stability. There was no error analysis, no theoretical work done for the error analysis, and some numerical experiments were conducted to compare the efficiency of the methods. Next, so this work by Connor Parrow and Martina Bukaj, this is very recent work. So over here, they devised the Cauchy theta-like method where they showed the method to be second order in time. Again, there was no time error analysis done. So how is our work different than theirs? So I will be defining a new scheme based on this auxiliary interface variable mu, which lives on the interface, which comes from the Robin boundary data condition. I will be showing my method to be unconditionally stable, as well as I'll be showing theoretically first order convergence in time for my scheme. And none of the work over here has shown that. And yeah, I'll be conducting some of the numerical experiments based on the schemes that I will be devising, which is the Robin and the iterative scheme and the monolithic scheme. Next, function spaces. So yeah, for Stokes variable, we have this VF for the fluid variable and WF for the fluid pressure. So we get all this from the partial differential equation and along with the boundary condition. For BO variables, we have VP for the Darcy velocity, WP for the Darcy pressure, and XP for the displacement. Again, we are using all the boundary condition. And we have some bilinear form. So I will be making use of these bilinear form in devising my numerical algorithm. And we get these bilinear form after multiplying the partial differential equation by the appropriate test function and doing integration by parts and applying all the boundary conditions. Next, so I'll be defining all these Robin transmission conditions on the interface. So these are very important to us because ultimately, I'll be defining an auxiliary scheme which is based on mu, which is this variable which lives on the interface. So yeah, using all these boundary conditions, I'll be defining my variable mu. So the first condition over here for the fluid subproblem. So you can see these are linear combination of the transmission conditions on the interface that I took. So in blue, we have the conservation of mass imposed, and in red, we have the conservation of momentum imposed. Similarly, the second equation over here, it's a linear combination of this conservation of momentum along with the no-slip Beaver-Joseph-Safman condition. Same way for the Beer-Sub problem, I'm taking linear combination of all these transmission conditions on the interface. So we have in blue conservation of mass along with conservation of momentum in red. Second, yeah, again, we have conservation of momentum in red and the no-slip Beaver-Joseph-Safman condition. And last, we have the conservation of mass in blue and along with the balance of normal fluid stress. So I'll be making use of all these Robin boundary conditions. Next, we have discretization in space. So for the fluid variables, I'll be taking insub-stable finite elements like Taylor-Hodon mini elements. For Darcy variables, I have stable mixed Darcy pairs, so I'll be making use of Ravetoma or BDM elements. And for displacement, we just needed to be conforming Lagrange finite element space. Now, discretization in time, I'll be making use of backward Euler discretization. Next, so now I'll be defining my Robin scheme. I will start by solving the fluid sub problem. So this algorithm over here, this comes from the equation, the partial differential equation of the fluid sub problem. So yeah, multiplying appropriate by appropriate test function and doing integration by parts. So you can see in red over here on the right hand side, we have the Robin boundary conditions for the fluid sub problem that I just explained. So yeah, these are the Robin boundary conditions which are imposed in a weak sense in the Stokes subproblem. So I will first solve my fluid problem. Then after obtaining the information about my fluid velocity and the fluid stress tensor, I will go on to solve my BO subproblem. So again, you can see on the right hand side, we have these BO subproblem Robin boundary condition imposed on the right hand side. So now over here, these are imposed at the same time step. So first we solve the fluid problem, then obtain the information of the fluid variable, then we go on to solve the BO problem, and all these boundary conditions, they're imposed in a weak sense. Okay, now I'll be defining my auxiliary interface variable, mu. So mu lives in the trace of the fluid velocity. So the normal and a tangential component of mu in a weak sense are defined using the fluid Robin boundary conditions. Why do I use fluid Robin boundary condition? Because I start my problem by solving the fluid subproblem. That's why I'm using these fluid Robin boundary conditions. Next, we have this Robin partition algorithm. First, I start, before starting my time stepping scheme, I obtain this information about the mu variable at the initial time by solving, by using all this Robin data. I go on, I start my time stepping loop, and then I solve my Stokes sub problem. And now over here, instead of all those variables which were there in the prototype version that I showed, now we have this good looking scheme which have these mu variables at the nth time step. Again, Robin boundary conditions are imposed in a weak sense. After solving the fluid sub problem, I go on to solve the BO sub problem. So again, we have these mu variables on the right hand side along with these fluid variables UF and the stress variable over here, which we just obtained the data for. So yeah, after solving the BO sub problem, I go on to update my mu variable because this is very important. I'm using this mu variable in both the sub problems, the Stokes and the BO sub problem. I update my mu variable at every time step like this. So I obtain these updates using the BO and the fluid subproblem Robin boundary conditions. So this was my whole scheme. And using this scheme, we have done a stability analysis. We were able to show that our method is unconditionally stable. Now, I'm not going to go on to discuss the proof for this, obviously, because this was like 4 or 5 pages long. But yeah, so over here, we get stability bound for fluid variable, for the structure velocity. And so you can see that the Darcy pressure is multiplied by S0. So S0 in realistic life can be very, very small. So we can lose this stability bond for Darcy pressure along with, you can see that the stability bond for mu variable is multiplied by delta T. So if delta T was to become extremely small, again, we will lose all these stability bound for delta T. So we need an improved stability bound. So and also over here, we do not have a stability bound for fluid pressure as well. So using these discrete in-soup conditions, we can obtain stability bound for the fluid pressure and for the Darcy pressure, because Darcy pressure was multiplied by S0, which can be extremely small. For mu n, we were not able to obtain the stability bound in L2 norm, but in H minus half norm using the L2 orthogonal projection and the Stokes discrete extension theorem, we can obtain an optimal stability bound for mu variable in H minus half norm. So this is another stability energy bound that we have over here. And this is an improved version which with all the bound for all the subdomain variables. Next, we have the type discretization error. So UI, PI, these are all the errors for the, for UI, it's the error for the velocity, PI is the error for the pressure, HP is the error for the displacement, and MN is the error for the mu variable that lives on the interface. So again, I'm not going to go into the proof for this error analysis. So we were able to get first order convergence in time. So some of the steps, they were similar to stability analysis. Yeah. Next, I'm going to define this iterative algorithm. So my numerical experiments will also be based on this. This is extremely important. So what happens in iterative algorithm is inside the time stepping scheme, I introduce an iterative scheme inside that. And now we are solving the fluid problem and the BO problem at every iteration. So you can see K is the iterative index. I begin by solving the Stokes problem, and then I go on to solve the BO problem. And this is happening inside the iteration loop. And now mu is updated at every iteration instead of at every time step. And at every iteration, we check the stopping criteria. If this is met, we go on to the next time step and again enter another iteration loop. And if it's not met, then we move on to the next iteration. Now I have this theorem for the convergence of iterative algorithm. So as k tends to infinity, all the subdomain variables, they go to these limit functions. And so we have convergence in the respective spaces. Now, using this convergence theorem, I'm gonna define another scheme. So this is a strongly coupled implicit scheme, monolithic scheme. So using the limit functions, we can solve this monolithic scheme over here. Again, this is important because this is the third algorithm that I've defined. I'll be using this one as well for the numerical experiments. Now over here, mu is not acting as an auxiliary interface variable. It's acting as a Lagrange multiplier where it's imposing this continuity conditions on the velocity over here. Okay, next we have the numerical results. So the first test we have is this normal convergence test, which I think most of the numerical analysis people, they do that. So yeah, taking all the model parameters equal to 1 and taking this exact solution to the problem. So we have this table for the non-iterative scheme. We have first order convergence in time. So you guys can see as delta t is decreasing, we are getting first order convergence in time for the non-iterative scheme. Next, so yeah, I ran another algorithm for the iterative scheme. Again, we were getting first order convergence in time. So the value of the errors, they decreased, but the order was the same actually. So yeah, so I'm going to be running my numerical experiments on iterative algorithm just with 10 iterations, because running on 100 iterations, this is making it very, very expensive. As you can see, it's taking so many iterations to run. Okay, now I have some convergence plots for just for comparison purposes. We have in green slope 1 and in red I have the non-iterative scheme, and rest of them you can see the iterative 10 version, iterative 100 version, and the monolithic scheme. We have the same plot because all the graphs. So yeah, running the numerical experiment was giving literally the same error. That's why these graphs, they coincide on towards each other. And you can see that the red one is above all rest of these schemes because we were getting slightly higher error for the non-iterative scheme. So these experiments were done for gamma equal to 1. And yeah, we have first order convergence for fluid velocity, Darcy velocity, and displacement. Okay, next I wanted to compare which values of gamma will work and which values of gamma will not work for different algorithms that I've defined. So you can see for gamma equal to 0.001 over here, the non-iterative scheme tends to lose convergence, right? Yeah, for all these variables. We do not have convergence for the non-iterative scheme for all these variables. However, if we were to run our algorithm just for 10 iterations or 100 iterations, like for rest of the schemes, we have first order convergence in time. Similarly, if I were to take a bigger value of gamma, like gamma equal to 100, again, non-iterative algorithm does not give us good results. Like it does not give us first order convergence in time. Rest of the algorithms, they're fine. We are getting first order convergence in time. Now, this is a robustness study that I did for different values, different orders of gamma. You can see that so the first row over here is for the non-iterative algorithm. So we can see for gamma equal to 0.001 and gamma equal to 100, basically the extreme values of gamma. If it's extremely small or if it's extremely large, the non-iterative algorithm does not perform well, whereas other values of gamma like 0.01, 0.1, 1, 10, it's fine. We are getting first order convergence in time. But when I ran the iterative algorithm, just with 10 iteration, you can see the second row, even with extreme values of gamma, we were getting first order convergence in time. Next is this blood flow application. So yeah, I ran this blood flow application for the fully dynamic Stokes-Biot problem. So yeah, I had to add this spring coefficient, the spring term over here. So omega F is the fluid region and omega P over here is the poroelastic structure region. And this right over here is the zoomed in version of the interface. I applied all these boundary conditions and yeah, all the body force terms and the external sourcing term, they were set equal to 0. I chose my parameters to be this. So you can see that the fluid velocity and the structure velocity, they are close to each other. So the ratio is close to 1. So this is a perfect regime for added mass effect. So yeah, over here, when you can see the first row is for the non-iterative scheme and the second row is for the monolithic scheme. We are getting a very good qualitative match. So this is the pressure wave. So this is the wave propagation happening for the fluid and RC pressure. You can see from left and right, you can see the wave propagating for different times. So yeah, we have a good match over here. The second figure over here is for the velocity, fluid and RC velocity. So these arrows represent the direction of the flow. And yeah, again, we have a good match over here between the non-iterative scheme and the monolithic scheme for different times. Okay, now I wanted to compare my fluid variables, some of the fluid variables and some of the bio variables at the interface for different algorithms. So you can see non-iterative algorithm between iterative and monolithic scheme, you can see that the graph they're coinciding, which makes sense because iterative scheme, it converges to the monolithic scheme. So we were getting literally the same values for the fluid pressure. And actually for all the variables, we were getting the same values for the iterative and monolithic scheme. So yeah, for the first time step, you can see there's a slight difference. And as time passes by, this difference kind of goes away, which is good. Similarly, the same pattern of behavior is observed for the vertical fluid velocity, and all these values, they were computed on the interface. Similarly, for the vertical Darcy velocity and for the vertical structure displacement, you can see for initial time step, there's a slight difference, but as time passes by, this difference kind of goes away. Now, I want to talk about the robustness study for the blood flow application. So like in the previous experiment, I was taking the value of gamma equal to 1000. Now I'm just taking different orders of gamma over here to see what kind of results I get on the interface and what kind of values I'm getting for all these fluid variables and the uh, and the BO variables. So you can see for gamma equal to 10, this graph is obviously deviating from rest of the graph. So this is a very, very small value that will not work for a blood flow application. Rest of the values, rest of the orders are completely fine. And same behavior is shown for vertical fluid velocity. You can see the graph for gamma equal to 10 is deviating way more than rest of the graph over here. So this value for gamma, like extremely small value of gamma, will not work because when I was defining my Robin transmission conditions on the interface, we need to make sure that all these transmission conditions like conservation of mass and conservation momentum, they are imposed properly. So when we choose a very, very small value of gamma, it means that we are not giving a good weight to that particular transmission condition and it's not imposed nicely, and that's why we can see this instability in the scheme happening. So yeah, same behavior for vertical Darcy velocity and the vertical structure displacement. Okay, now summary of what we have done. We developed Robin-Robin splitting method for the Stokes-Biot FPSI model. using this interface auxiliary variable, which we define using the Robin boundary conditions. Non-iterative scheme, we did theoretical analysis on that. We were able to show unconditional stability and first order convergence in time. Iterative scheme, we showed that this converges to a new monolithic scheme and a strongly implicit coupled scheme where Robin parameter is now acting, sorry, this Robin variable is now acting as a Lagrange multiplier, which enforces velocity continuity. And yeah, this method can be used for FSI instead of FPSI. Okay, future outlets. So future studies can be done on parameter robustness. So in this paper, we have already only talked about the robustness of this Robin parameter gamma. We can talk about other parameters like what happens, like which orders of Lame parameters will work, something like that. Robin methods for the mixed elasticity formulation. So our next project is based on this scheme. Like we'll be taking mixed elasticity scheme. There will be more variables, but it's much better for us because now we don't have to compute like stress tensors explicitly. So like stress tensors in this scheme will be acting as a normal variable, and there will be extensions to Navier Stokes-Biot. So this is something which can be done in the future. We've not discussed about this. So yeah, if anyone wants to work with Professor Ivan Yotov, I'm sure yeah, and one of his future projects will be based on that. Yeah, and yeah, I would like to thank NSF for giving us grant for this funding. And yeah, our paper is available on archive if anyone wants to take a look. And yeah, if anyone has doubts, please reach out to me. This is my email ID and this is my office. And thank you so much for bearing with me and listening to me. And do we have any questions from the audience?
Yeah, I have a question.